Hello, in this lecture we will find the radius of the small circle. In the picture we have two circles with internal length between them at this point. Let's call this point point N. Point N is the point of contact between those two circles. They touch each other at point N. And we also know that AB is the diameter of the big circle, and this is the right angle, and also this angle equals to 90 degrees. And the small circle has three tangents. This tangent is tangent to the small circle at this point. Let's call this point point S. Point S is the launch point between the tangent and the circle, or the point of tangency between the tangent and the circle. And also we have the second tangent that is tangent to the circle at this point. Let's call this point point Z. Point Z is the launch point between the tangent and the circle, or the point of tangency between the tangent and the circle. And we also have the third tangent to the circle. This tangent is tangent to the small circle at this point. Let's call this point point M. Point M is the launch point between the circle and this tangent, or point M is the point of tangency between the tangent and the circle, between this tangent and the circle. Okay, so first of all, we will define the center of the small circle as point Q. Again, point Q is defined as the center of the small circle, and point P is defined as the center of the big circle. So I will write it down. Point P is the center of the small circle. Point Q is the center of the small circle. Point Q is the center of the small circle, and point P is the center of the big circle. So I will read again the things that I wrote. Point Q is the center of the small circle. This is point Q, and point P is the center of the big circle. This is point P, the center of the big circle. Okay, and we will define small r is the radius of the small circle, and capital R is the radius of the big circle. I will read again the things that I wrote. Small r is the radius of the small circle, and capital R is the radius of the big circle. Okay? So, in the next step, we will draw 3 radiuses of the small circle that exit from the center of the circle and touches the circle at the launch points between its tangent and itself. Okay, so the first radius will exit from the center of the circle, that is to say from point Q, and it touches the circle at the launch point between the circle and its tangent. Okay, so this is the first radius. Then I will draw the second radius that exits from the center of the circle and touches the circle at point Z, that is the launch point between the circle and this tangent. Okay, this is the second radius, and I will draw the third radius that exits from the center of the circle from point Q and touches the circle at point M, that is the launch point between the circle and this tangent. Okay, actually we know that this angle is a right angle, and we have here a straight line of the diameter AB, so this angle also must be equal to 90 degrees because of the fact that along a straight line on the upper side the sum of the angles equals to 180 degrees, and if this is a right angle, this angle must be also a right angle, because the sum of the angles on a straight line, on the upper side of a straight line, equals to 180 degrees. And from the same reason, this is also must be a straight line. So actually we have a rule. Rule number 1, and rule number 1 states that a tangent to the circle is perpendicular to the radius at the launch point. So I will read rule number 1 again. Rule number 1 states that a tangent to the circle is perpendicular to the radius at the launch point. Okay, so actually whenever you draw a radius that is drawn to the launch point, actually it touches the launch point like here, then the tangent will be perpendicular to that radius. That is to say, this angle is a right angle, because of the fact that this radius touches the launch point, that is point Z. It is drawn to the launch point and also touches the launch point. Therefore, this is a right angle because the radius is perpendicular to the tangent and the tangent is perpendicular to the radius. And also, this is according to rule number 1. And also we have here that radius that is drawn to the launch point, actually it touches the launch point. Therefore, according to rule number 1 that states that a tangent to the circle is perpendicular to the radius at the launch point. So this radius touches the launch point, it is drawn to the launch point and it touches the launch point, that is point M. Therefore, according to rule number 1, the tangent is perpendicular to that radius, that is to say this is a right angle and also this is a right angle. So whenever you draw a radius that is drawn to the launch point and touches the launch point, then that radius will be perpendicular to its tangent. Okay? And also we have the third radius that is drawn to the launch point, that is point S, and it actually touches the launch point. Therefore, that radius is perpendicular to the tangent, and you can also say that the tangent is perpendicular to that radius, it is exactly the same thing to say that the tangent is perpendicular to the radius, so the radius is perpendicular to the tangent, it is the same thing. So whenever a radius is drawn to the launch point, then that radius will be perpendicular to the tangent. Okay? So actually, if we look at quadrilateral QZMD, we will focus on quadrilateral QZMD. Okay, on quadrilateral QZMD, this quadrilateral has three right angles. This is the right angle, this is the right angle, and also this is the right angle. Okay, quadrilateral QZMD has three right angles. That the sum of them equals to 3 times 90 degrees is 270 degrees. Okay, the sum of these three right angles is equal to 270 degrees, because 3 times 90 degrees equals to 270 degrees. Okay, and we have rule number 2. That states that the sum of the angles in a quadrilateral equals to 360 degrees. Okay, this rule number 2 states that the sum of the angles inside a quadrilateral equals to 360 degrees. I will read rule number 2 again. Rule number 2 states that the sum of the angles inside the quadrilateral equals to 360 degrees. So, according to rule Number 2, the sum of the angles inside quadrilateral, this quadrilateral QZMD must be equal to 360 degrees. So therefore 270 degrees, that is the sum of the three angles of this quadrilateral plus the size of the fourth angle that we define it as y. Y is the size of the fourth angle, the size of the fourth angle. Again, y is defined as the size of the fourth angle, so 270 degrees plus y must be equal to 360 degrees according to rule number 2, that states that the sum of the angles inside a quadrilateral equals to 360 degrees. Okay, we have this equality that states that in quadrilateral QZMD the sum of the angles must be equal to 360 degrees. That is to say, the sum of the three angles plus the sum of the fourth angle must be equal to 360 degrees according to rule number 2. Okay, so here we will subtract 270 degrees from this equality, and we will get that y equals to 90 degrees. Okay, so the size of the fourth angle must be equal to 90 degrees. Therefore, this angle is also a right angle. So actually, quadrilateral QZMD has 4 right angles. As you can see here in the drawing, this quadrilateral QZMD has 4 right angles, and we have rule number 3 that states that if a quadrilateral has 4 right angles, then it is a rectangle. rule number 3 again. Rule number 3 states that if a quadrilateral has 4 right angles, then it is a rectangle. So, according to rule number 3, quadrilateral QZMD is a rectangle because it has 4 right angles. This quadrilateral QZMD is a rectangle because it has 4 right angles. So according to rule number 3, quadrilateral QZMD is a rectangle. Okay, quadrilateral QZMD is a rectangle according to rule number 3. Okay, but we have also rule number 4 that states a rectangle as the opposite sides of a rectangle are equal to each other. So I will read rule number 4 again. According to rule number 4, the opposite sides of a rectangle are equal to each other. So actually, according to rule number 4, QZ equals to MD, because QZ is opposite to MD, side QZ is opposite to side MD, therefore QZ equals to MD, according to rule number 4. According to rule number 4, that the opposite sides of a rectangle are equal to each other. Okay, QZ equals to MD according to rule number 4. QZ equals to MD. But QZ is the radius of the small circle, it equals to small r. So we can add here that QZ equals to the radius of the small circle, that is to say it equals to small r. Okay, QZ is the radius of the small circle. Okay, so we can derive from this equality that MD equals to small r. Okay, MD equals to small r. Okay, so I write it down that MD equals to small r. So here MD equals to small r. Okay, so in the next step we have quadrilateral SQCM, this quadrilateral, and we will repeat on the same process in order to prove that CM also equals to the radius of the small circle, because it is exactly like quadrilateral QZMD, because quadrilateral QSMC has 3 right angles, 1, 2, 3. Therefore, the fourth angle must be equal also to 90 degrees because of the rule number 2 that states that the sum of the angles in a quadrilateral equals to 360 degrees. So this is a right angle. And we have rule number 3 that states that if a quadrilateral has 4 right angles, then it is a rectangle. So quadrilateral QSCM has 4 right angles, 1, 2, 3, 4. Therefore, according to rule number 3, quadrilateral QSCM is a rectangle. And we have rule number 4 that states that the opposite sides of a quadrilateral are equal to each other. That is to say, QSCM, that is rectangle, the opposite sides of it are equal to each other. That is to say, QS equals to CM, according to rule number 4. But we know that QS equals to the radius of the small circle. For that reason, CM that equals to QS also will be equal to the radius of the small circle. That is to say, it equals to small r. Okay, so CM also equals to small r. Okay, so we concluded that MP equals to small r and CM also equals to small r. In the next step, we will define PM as x, that is to say PM equals to x, and what is the size of line segment CP? CP actually equals to CM minus PM. Again, CP, this line segment, equals to CM minus PM, or CP equals to CM, that is small r, minus PM, that is x, according to our definition. So in total, CP equals to small r minus x. Okay, CP equals to small r minus x. Okay, and in the next step we will calculate the radius of the big circle in 2 different ways. We know that P is the center of the big circle, therefore the radius of the big circle equals to AP, from one side, but the radius of the big circle also equals to PB from the other side, because actually AB is the diameter of the big circle. Therefore, AP, that is the center of the big circle, equals to the radius. AB, that is the diameter of the big circle, that it equals to 2 times the radius of the circle. That is to say, it equals to 2 times capital R. It actually equals to AP, that is R, plus PB, that is also capital R. Okay, so we will create two expressions for the radius of the big circle. From one side, AP will be equal to capital R, and from the other side, the second expression for the big circle will be PB, that also equals to capital R. Okay, so our first equation and expression for the radius of the big circle will be the simple expression that states that AP equals to capital R, that is the radius of the big circle, and our second expression for the radius of the big circle will be that the radius of the big circle equals to PB, or PB also equals to the radius of the big circle. This will be our second equation. PB also equals to the radius of the big circle. Okay, so we'll return to equation number 1 that states that AP equals to the radius of the big circle, but what is the value of AP? AP equals to AC plus CP. Again, AP equals to AC plus CP. Okay, AP equals to AC plus CP. And what is the value of AC? AC equals to 9 units because it is given us in the question. And what is the value of CP? CP equals to small r minus x. Okay, CP equals to small r minus x. So in total we got that AP that equals to the radius of the big circle equals to 9 plus small r minus x. So I will write it again, that the radius of the big circle, according to equation number 1 and also expression number 1, the radius of the big circle equals to 9 plus small r minus x. Okay, so that will be our second equation, our first equation and first expression for the radius of the big circle, and our second expression and equation for the radius of the big circle will be the second expression and equation that PB equals to the radius of the big circle, that is to say it equals to capital R. PB equals to capital R, the radius of the big circle. But what is the value of PB? PB equals to PM plus MD plus DB. Okay, again, PB equals to PM plus MD plus DB. Okay, PB equals to PM plus MD plus DB. Okay, so what is the value of PM? PM equals to X according to our definition, plus MD. What is the value of MD? MD equals to R according to what we have already found, that MD equals to small r, that is the radius of the small circle. And what is the value of dB? dB equals to 4 units. It is given us in the question. So in total we got that PB, that equals to the radius of the big circle, equals to X plus small r plus 4. So I will write it again, that the radius of the big circle according to the second equation and expression equals to X plus small r plus 4. Okay, that is the second expression and second equation for the radius of the big circle. Actually, we have here two expressions and equations for the same radius, the radius of the big circle. So of course they are equal to each other, so we will compare expression number 1 to expression number 2. That is to say, we will create equation number 3 that states that capital R according to equation number 1 equals to capital R according to equation number 2. Okay, so we will do it now. Equation number 3 states that capital R, that is the radius of the big circle, according to equation number 1, it is 9 plus small r minus x equals to capital R according to equation number 2, that is actually x plus small r plus 4. Again, here we created equation number 3 that states that capital R according to equation number 1 equals to capital R according to equation number 2, or capital R equals to capital R. Okay, so here in equation number 3 we have R on this side of the equation and we have R on the other side of the equation, so we can cancel R. So what left after we cancelled R is nine minus x equals to x plus 4. So what is left after we cancelled R is 9 minus x equals to x plus 3. Here we will subtract 4 from this equality and we will get that 9 minus 4 is 5. Minus x equals to x. Okay. After we subtracted 4 from this equality, we got that 5 minus x equals to x. Here we will add x to this equality, and we will get that five minus x plus x is 5, and x plus x is 2x. So we got this equality that states that 5 equals to 2x. Here we will divide this equality by 2 in order to get the value of x. Okay? So x equals to 5 over 2. 5 over 2 is 2.5 units. So we got the value of x equals to 2.5 units. We have equation number 1. According to equation number 1, the radius of the big circle equals to 9 plus small r minus x. Okay, that is equation number 1. It states that capital R equals to 9 plus r minus x, but we have already found out that the value of x is 2.5 units, so we can substitute x by 2.5 units, and what we will get is that capital R equals to 9 plus small r minus 2.5. Okay, so here 9 minus 2.5 is 6.5, so in total we will get that capital R equals to 6.5 plus small r. Okay, so actually equation number 1 says that the radius of the big circle is bigger by 6.5 units than the radius of the small circle. Okay, and we already know that x equals to 2.5 units. Okay, so in the next step I will present a rule number 5, and we will implement rule number 5 in our two circles. Rule number 5 states that if two circles touch each other internally, if two circles have internal lunge between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so I will read rule number 5 again. Rule number 5 states that if two circles have an internal lunge between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so the meaning of rule number 5 is that if two circles touch each other internally, then the distance between their centers, that is to say, if we define the distance between their centers as d, then according to rule number 5, the distance between their centers is equal to the difference between the lengths of their radiuses. That is to say, d equals to, if r1 is the radius of the big circle and r2 is the radius of the small circle, then according to rule number 5, d equals to r1 minus r2. Okay, so we actually can implement rule number 5 in our two circles, because here we have two circles that have internal lunge between them at point N. Therefore, according to rule number 5, the distance between their centers, we know that the center of the small circle is at point Q and the center of the big circle is at point P. So the distance between those two centers is QP. And QP equals to, according to rule number 5, QP equals to the difference between their radiuses. That is to say, QP equals to capital R minus small r. Okay, so I'll write it down. So here we have equation number 4 that states that the distance between the centers of the circles, that is QP, this distance QP equals to the difference between their radiuses, equals to capital R minus small r. Okay, so equation number 4 is the implementation of rule number 5 in our two circles. So here we can add minus r, we can add r to both sides of the equation. We can add r to equation number 4, and we will get that capital R equals to QP plus small r. Okay, we have this expression for the radius of the big circle, but we have also expression number 1 for the radius of the big circle. According to expression or equation number 1, the radius of the big circle equals to 6.5 units plus small r. Okay, we have two different expressions and equations for the radius of the big circle. So because of the fact that that is the same radius, of course those two expressions are equal to each other, so we can write down expression or equation number 5 that states that the radius according to expression number 1 equals to the same radius according to expression number 4. Okay, so equation number 5 states that the radius according to equation and expression number 1, the radius of the big circle, that is 6.5 plus small r, equals to the radius of the same radius of the big circle according to equation number 4, that is qp plus small r. Again, equation number 5 states that the radius of the big circle according to expression number 1 equals to the radius of the same big circle according to expression number 4. Okay, so here we have r on this side of the equation and we have r on the other side of the equation, so we can cancel r. And after we cancel r, what is left is qp equals to 6.5 units. Okay, we found out the value of qp, that is actually the distance between the centers of the two circles. This distance equals to 6.5 units, and we have already found out that x equals to 2.5 units. Okay, so we found out the values of qp and x. So in the next step we will connect together points q and p by a straight line. So actually we have here triangle, the green triangle QMP is a right triangle because of the fact that angle QMP is a right angle. Okay, so we will focus on the right triangle QMP. And in the right triangle QMP, we can implement the Pythagorean theorem in order to find out the value of QM, that is the radius of the small circle. We know that QP equals to 6 that is the hypotenuse of the green triangle, equals to 6.5 units, and PM, that is x, equals to 2.5 units. So the only missing variable that we have is QM, that is the radius of the small circle, and we will find the radius of the small circle according by the implementation of the Pythagorean theorem on the green right triangle. According to the Pythagorean theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here the square of the hypotenuse is QP square equals to the sum of the squares of the perpendiculars equals to QM square plus PM square. Okay, so I'm writing down according to the Pythagorean theorem. the square of the hypotenuse is QP square equals to the sum of the squares of perpendiculars equals to QM square plus PM square. Okay. This is the implementation of the Pythagorean theorem in the right triangle QMP. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. We have already found out that QP equals to 6.5 units and QM, that is X, equals to 2.5 units. And actually PM is the radius of the, or QM is the radius of the small circle. So QP square is 6.5 square equals to QM square, that is 2.5 square, minus PM is 2.5 square, and QM is the radius of the small circle. So okay, QM is the radius of the small circle and PM equals to 2.5 units. So in total we got that 6.5 square equals to 2.5 square plus r square. 6.5 square equals to 42.25 and 2.5 square equals to 6.25. So I write it down. So in total we got that 42.25 equals to 6.25 plus r square. Here we can subtract 6.25 from this equality and we will get that 42.25 minus 6.25 is 36. So 36 equals to r square. So we have this equality. Here we will take a root out of this equality and we will get that the radius of the big circle equals to the root of 36. The root of 36 is 6, so the radius of the big circle equals to 6 units. The radius of the small circle equals to 6 units. 6 units. Again, the radius of this small circle, that is to say small r, equals to 6 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the radius of this small circle, and we have here two circles with an internal lunge between them at point N. They touch each other at point N, and we have the small circle that has 3 tangents to it, 1, 2 and 3. The lunge point between this tangent and the circle is at point Z. The lunge point between this tangent and the circle is at point S, and the lunge point between the circle and this tangent is at point M. And we also know that AC equals to 9 units, PD equals to 4 units. This is a right angle and this is also a right angle. First of all, if this is a right angle and AB is the diameter of the circle, then this is also must be equal to 90 degrees because of the fact that along a straight line in the upper side, the sum of the angles must be equal to 90 degrees. So if this angle is 90 degrees, this angle also must be equal to 90 degrees and also here we have here 90 degrees. So this angle must complete the total sum of the angles here to 180 degrees. So this angle must be equal also to 90 degrees. Okay, and we actually draw 3 radiuses of the small circle that exit from the center of the circle, that is to say exit from point Q, that is the center of the circle, and touches the circle at the launch points. This radius touches the circle at the launch point, that is to say at point Z. This radius touches the circle at the launch point, that is to say point S, and this radius also touches the circle at the launch point, that is point M. Okay, and actually we have a rule, that is rule number 1. According to rule number 1, a tangent to the circle is perpendicular to the radius at the launch point. Okay, so whenever you draw a radius that is drawn to the launch point, then that radius will be perpendicular to the tangent. That is to say, this is a right angle. Here also we have a radius that is drawn to the launch point. Actually it touches the launch point, that is point S. Therefore, according to rule number 1, this radius is perpendicular to the tangent. That is to say, this is a right angle. And also we have the third radius that is drawn to the launch point, that is point M. Actually it touches the launch point, point M. Therefore, according to rule number 1, this is the right angle, and also this is the right angle because the radius is perpendicular to its tangent. Okay, so actually if we focus on quadrilateral QZMD, here we have 3 right angles, 1, 2, and 3, and that sum of them is 90 degrees times 3 is 270 degrees, and we have rule number 2 that states that the sum of the angles inside a quadrilateral equals to 360 degrees. So, and especially in quadrilateral QZMD, the sum of its 4 angles must be equal to 360 degrees according to rule number 2. So the sum of the 4 angles of quadrilateral QZMD is the sum of the 3 angles, that is 90 times 3 is 270 degrees, plus the size of the 4th angle, that is Y, must be equal to 360 degrees. So we have this equality according to rule number 2 that states that the sum of the angles in any quadrilateral equals to 360 degrees. So the sum of the 3 angles, that is 270 degrees, plus the size of the 4th angle must be equal to 360 degrees according to rule number 2. So here we subtracted 270 degrees from this equality and we got that Y equals to 90 degrees. So the 4th angle is also a right angle. This is also a right angle in quadrilateral QZMD. And we have also rule number 3 that states that if a quadrilateral has 4 right angles, then it is a rectangle. So quadrilateral QZMD has 4 right angles, 1, 2, 3, and 4, and therefore according to rule number 3, quadrilateral QZMD is a rectangle. Okay, so this is a rectangle, and we have rule number 4 that states that the opposite sides of a rectangle are equal to each other. So in this rectangle, the opposite sides are equal to each other according to rule number 4. That is to say, QZ that is opposite to MD, QZ equals to MD. According to rule number 4, side QZ equals to MD because they are two opposite sides, so they are equal to each other according to rule number 4. But we know that QZ is the radius of the small circle. QZ is the radius of the small circle, it equals to capital R. QZ equals to capital R. So from this equality, you can deduce that MD equals to small r. Okay, so the size of MD is small r. And we repeated on the same process in order to prove that CM also equals to small r, because actually we have here quadrilateral QSCM that has 3 right angles. So according to rule number 2, the fourth angle must be equal also to 90 degrees. And according to rule number 3, this quadrilateral must be a rectangle. And according to rule number 4, the opposite sides of this rectangle are equal to each other. So QS equals to CM. But QS equals to small r. So CM must be also equal to small r. So actually CM equals to small r. And MD also equals to small r. Then we defined PM as x. So CP must be equal to CM that is small r minus PM that is x. That is to say CP equals to small r minus x. And then we created two equations for the radius of the big circle. AB is the diameter of the big circle, that is to say it equals to 2 times the radius of the big circle, and actually the radius of the big circle equals to AP. Okay, and the radius of the, so that is equation number 1, that capital R equals to AP. And equation number 2 states that the radius of the big circle equals also to PB. So capital R equals to PB is the second equation. Okay, we have those two equations for the radius of the big circle, and the radius of the big circle equals to capital R, and capital R equals to AP, AP equals to AC plus CP, but AC equals to 9 units and CP equals to minus small r minus x. So in total AP will be equal to 9 plus small r minus x. So according to equation number 1, the radius of the big circle equals to 9 plus small r minus x. And we also have the second equation that states that the radius of the big circle equals to PB. But what is the value of PB? PB equals to PM plus MD plus DB. PM equals to X, DB equals to small r, MD equals to small r, and DB equals to 4. So in total we got that the radius of the big circle according to equation number 2 equals to x plus small r plus 4. So we have two different expressions for the same radius. Of course they are equal to each other. So equation number 3 states that the radius of the big circle according to equation number 1 equals to the radius of the big circle according to equation number 2, or capital R equals to capital R. And from equation number 3 we got the value of x. We found out that x equals to 2.5 units. Okay, but we have equation number 1 that states that the radius of the big circle equals to 9 plus small r minus x, and we have already found out that x equals to 2.5 units. So we can substitute x by 2.5 units, and we substituted x by 2.5 units, and we found out that the radius of the big circle equals to 6.5 plus small r, and we have already found out that x equals to 2.5 units. Then we presented rule number 5, and we implemented rule number 5 in our two circles. According to rule number 5, if two circles touch each other internally, or if two circles have internal lunge between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So if two circles touch each other internally, then the distance between their centers, if the distance is d, must be equal to the difference between their radiuses. If R1 is if R1 is the radius of the big circle and R2 is the radius of the small circle, then D must be equal to R1 minus R2 according to rule number 5. So we implemented rule number 5 in our two circles, because here we have two circles that have internal lunge between them at point N. So according to rule number 5, the distance between their centers, that is to say QP, must be equal to the difference between their radiuses, and the difference between their radiuses is capital R minus small r. So in total we got that according to rule number 5, QP, that is the distance between the centers of the two circles, must be equal to capital R minus small r. So from equation number 4 we got that capital R equals to QP plus R, and from equation number 1 we know that capital R equals to 6.5 plus small r. So because equation number 4 and equation number 1 are two different expressions for the same radius, again because equation number 1 and equation number 4 are two different expressions for the same radius, of course they are equal to each other. So we can compare equation number 4 to equation number 1 and create equation number 5 that states that capital R according to equation number 1 equals to capital R according to equation number 4. That is equation number 5, and from equation number 5 we got that QP equals to 6.5 units, and we have already found out that X equals to 2.5 units. Okay, then we connected together points Q and P by a straight line, and we got the green triangle. It is a right triangle because of the fact that angle QMP is a right angle. Therefore, triangle QMP is a right triangle. So we can implement the Pythagorean theorem in the right triangle QMP. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, QP square equals to QM square plus PM square. Okay, QP square equals to QM square plus PM square. We know that QP equals to 6.5 units. qm equals to x that equals to 2.5 units, and the only missing variable is the radius of the small circle. So we put the data inside this equality and we got the radius of the small circle. We found out that the radius of the small circle equals to 6 units. Again, the answer to the question is that the radius of the small circle equals to 6 units, so small r equals to 6 units. Okay, thank you very much.